Now let us look at what is handshaking theorem, or you can say the handshaking lemma. Now this handshaking theorem says that let G, V, E be an undirected graph with M edges. Then 2M is equal to summation V belongs to vertices degree of V. It means that the sum of degree of all vertices is twice the number of edges, because if M is representing the number of edges, okay, and this is the sum of degree of all vertices, sum of degree of all vertices. So this handshaking lemma theorem or handshaking lemma says the sum of degree of all vertices is twice the number of edges in the graph. Okay, for example, let us say this is the graph, this is the vertex v1, this is vertex v2, and this is representing the vertex v3, and these are the edges that we have. Now what is the degree of vertex v1? Degree of vertex v1 is 2. What is the degree of vertex v2? It is 2. What is the degree of vertex v3? It is also 2. So if I say the sum of degree of all vertices, that is we are adding degree of vertex v1 plus degree of vertex v2 plus degree of vertex v3, that should be equivalent to twice the number of edges. So twice the number of edges. Okay, so how many edges are there? There are 3 edges. This is edge e1, this is edge e2, and this is representing edge e3. So the sum of degree of all vertices, that is 2 plus 2 plus 2, degree of vertex v1 plus degree of vertex v2 plus degree of vertex v3 should be equal to 2 into the number of edges, which is equal to 3. So you can say the sum of degree of all vertices should be equal to twice the number of edges, that is represented by the handshaking theorem. Now this one more thing that you can say just by looking at this handshaking theorem, that is that number of odd vertices, the number of odd vertices in a graph is always even, okay. Why you can say the number of all odd vertices in a graph is always even? Just by looking at this particular theorem. Now for example, this theorem is saying the sum of degree of all vertices is twice the number of edges, correct? Now we can have a graph where the degree of a vertex can be odd or degree of vertex can be even, correct? Now for example, let us say this is a graph which is having 4 edges. This is, so 4 vertices, vertex v1, vertex v2, vertex v3, and vertex v4. So vertex v1, the degree of vertex v1 is 3, the degree of vertex v2 is 2, the degree of vertex v3 is 3, the degree of vertex v4 is 4, it is 2. Now here we have 2 vertices, that is the vertex v1 and the vertex v3, both are having odd degree, correct? So in a graph we can have a vertex which is having odd degree, or we can have a vertices which is having even degree. So this entire number, this can also be submitted this way: the sum of degree of vertices where degree is odd plus sum of degree of vertices where degree is even, right? So do you understand this? Are you following what I'm saying? I'm saying we understand the formula that sum of degree of all vertices is equal to twice of number of edges, but that sum of degree, that graph may be having odd degree as odd, and the graph may be having degree as even. So in total, when I'm saying summation of degree, that contains both the odd degree vertices plus both the even degree vertices. Now if we add both of them, then that will be equal to 2e, that is twice the number of edges. Now this summation, that is summation degree of even vertices. Now because degree is always even, because here the degree is always even, so we are always going to get even even number here. We are always going to get even number. That means if we add the sum of degree of all vertices where the degree is even, so we can have even number here. But here, because it is an odd number, so if we have odd vertices, with odd degree, then we can get an odd number. Otherwise, if we have even vertices, even number of vertices with even degree, with odd degree, then we can get a even number. Do you understand what I'm saying? I'm saying that again I'm repeating, sum of degree of all vertices is equal to twice the number of edges, correct? Now this sum of degree can be divided into two parts. One is the vertices which are having odd degree plus the vertices which are having even degree. So for example, here in this particular case, there are two vertices which are having odd degree and there are two vertices which are having even degree. The sum of degree of all vertices will be the degree of odd vertices plus the degree of even vertices, correct? Now this degree of even vertices is always going to give an even number, because it is we are making a sum of even numbers only, so this is always going to give an even number. But if the degree of odd vertices are there, now this can be an odd number or this can be an even number. Why it can be an odd number? If there are odd number of vertices, with odd degree, now this can give an odd number. If there are odd number of vertices with even degree, if there are even number of vertices with odd degree, again I'm repeating, if there are even number of vertices with odd degree, then we can get an even number, correct? Now this is always even, this number is always even, this number can be odd or it can be even, but we are always getting an even number here, because here you can see we have 2 into e, so we are always getting an even number. So because it is even, so the second number, it has to be even, it has to be even, it can never be odd, see, this is an important result, it can never be odd. It means we have the vertices which are having odd degree are always even, the vertices which are having odd degree are always even, the vertices which are having odd degree, or can say the number of vertices which are having odd degree is always even in graphs. Okay, do you understand what I'm saying? The vertices which are having odd degree is always even in graphs. So that is called as the handshaking theorem, or you can say the handshaking lemma. So the same result that I'm saying, the undirected graph has even number of vertices of odd degree, that we just proved, correct? Now look at this one. Here in this diagram they are saying, in a graph with directed edges, the in degree of a vertex v, which is denoted by d minus, is a number of edges with v, the terminal vertex as their terminal vertex, and the out degree of v is denoted by d positive, is the number of edges with v as the initial vertex. Okay, they are just telling what is the in degree and out degree. Now for example, if I say this particular node, now what is the in degree here? In degree, that is represented by d minus, okay, d minus in this vertex c. In degree means that what is the number of vertices which are in degree, which are coming inside. So here this is the edge that is coming inside, and this is the edge that is coming inside, and this is the edge that is coming inside. So for C, the in degree is 3, correct? Now if I say what is the out degree of C, out degree is represented by plus sign. So for C, what is the out degree? That is, this is the out degree and this is the out degree, so it is 2. Okay, so in degree of C is 3 as well as the out degree of C is 2, correct? Now in the same way, if I say for vertex D, for vertex D, the in degree is represented by d minus. So what is the in degree? That is the number of edges that is coming inside. This is coming inside, this is coming inside, so in degree of D is 2. And what is the out degree? That is represented by d plus for D. And what is the out degree? So this is going out and this is also going out, so the out degree is also 2 for this D. Correct? Now you understand what is the in degree for a graph and what is the out degree for a graph. Okay, now here they are saying let graph G is equal to V comma E be a graph with directed edges, then the sum of in degree of a vertex V is equivalent to the sum of out degree of a vertex V, which is equivalent to the number of edges, Now this is an important result. Let me tell you what this result is saying. Assuming that we have this graph, this is the vertex A, this is the vertex B, this is the vertex C, and this is the vertex D. And this is a directed graph because they are saying it is a directed edge. So this is a directed graph. So there must be some kind of directions that are given. So we can have assuming these directions. Some random directions I am taking. Correct? And we have one self loop also. Now they are saying the summation, if we add all the in degrees for a vertex V, for all the vertex V, that should be equivalent to the sum of all the out degrees. Correct? Now for example, if I say for the vertex A, what is the in degree? In degree for the vertex A is the number of edges that is coming inside A. So there's only one edge that is coming inside A, and that one edge is represented by this. So for in degree for A is 1. In the same way, what is the in degree for D? In degree for D is 2. Why? Because this is also coming inside and this is also coming inside. Correct? Now what is the in degree for C? So in degree for C is 1. What is the in degree for B? So what is the in degree for B? This is coming inside, as well as this self loop is also coming inside, so it is also 2. So what is the in degree of all these vertices? That is 1 plus 2 plus 1 plus 2, which is representing a total of 6. Correct? In the same way, if we add the out degree, so what is the out degree for vertex A? So out degree for vertex A is the edges that is going outside A, which is only this edge. So there is only one edge which is going out, so it is 1. What is the out degree for vertex B? So there's 2 edges which are going out, so out degree for vertex B is 2. What is the out degree for vertex C? So out degree for vertex C is represented as 2 because this is also going outside, this is also going outside. And what is the out degree for vertex D? So out degree for vertex D is represented by 0. Now this is a small mistake here. For in degree out degree for vertex A is 2, because for A this is also going out and this is also going out. So the out degree for vertex A is also 2. So if we add all these numbers, it will become 2 plus 2 plus 2, which is representing 6. Okay, so the in degree for all in this particular graph, the in degree for vertices is 6, which is equivalent to the out degree for the vertex. And if you count the number of edges, there is 1 edge, 2 edge, 3 edge, 4 edge, 5 edge, and 6 edge. Therefore the number of edges is also 6, that is also same. Correct? Now this is a theorem. Now let us look at the next theorem here. Now here in this graph they are saying what is a complete graph. So a complete graph on vertex n denoted by kn. Complete graph is denoted by this symbol. So most of the time in examination hall they are just going to give you this terminology or this symbol. It is a simple graph that contains exactly one edge between each pair of distinct vertices. Exactly one edge between each pair of distinct vertices. Now for example, this is a complete graph with only one vertex. This is a complete graph with 2 vertices, complete graph with 3 vertices, complete graph with 4 vertices, complete graph with 5 vertices, complete graph with 6 vertices. Okay, so if this is representing the number of vertices, and this is representing the number of edges. Okay, so if the number of vertices is 1, so number of edges are 0. If the number of vertices is 2, the number of edges in a complete graph is 1. If the number of edges is 3, the number of vertices in a complete graph is 3, the number of edges is also 3. Okay, so see, complete graph means we should have an edge between every pair of vertex. If the number of edges are 4, if the number of vertices are 4, the number of edges are 1, 2, 3, 4, 5 and 6. There are 6 edges. If the number of vertices are 5, then how many edges are there? That is 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. So there are 10 edges. If the number of vertices are 6, then you can count what is the number of edges that are present for this given graph. Now you have to tell if the number of vertices are n, then what will be the number of edges in a complete graph. Correct? Now this can be easily found out by doing this addition. Now you can see this is 0 and 1. So difference between these two terms is 1. Difference between these two terms is 2. Difference between these two terms is 3. This is 3. Difference between these two terms is 4. The difference between the next terms should be 5. So for 6 vertices, there should be 15 edges. So the difference is always coming out to be a natural number. Okay, right? So if I say what should be the number of vertices in a complete graph with n vertices, that should be n into n minus 1 divided by 2. Now let us prove this. So if we represent this n into n minus 1, that is 1 into 1 minus 1 divided by 2, which is equivalent to 0. Represent this one, it is 2 into 2 minus 1 divided by 2, which is representing 1. Now for this case, it is 3 into 3 minus 1 divided by 2, which is representing 3. For this case, it is 4 into 4 minus 1 divided by 2, which is representing 6, right? So if we have a total of n vertices in a complete graph, the number of edges should be n into n minus 1 divided by 2. That is here that we studied the complete graph. Now this is representing a cycle. A cycle Cn consists of n vertices v1 to vn and edges v1, v2 and v2 to v3 and up to so on vn minus 1 to vn. The cycles are represented like this. I think this is very simple and intuitive and I don't have to explain this one. Next is a wheel. Again, it is also very intuitive. It is always having a cycle, but there's one vertex in middle. Always there's a cycle and there's one vertex in the middle. Now this is representing a wheel. Okay. Now the next is saying what is a bipartite graph. A simple graph G is called as a bipartite if its vertex V can be partitioned into two disjoint sets v1 and v2 such that every edge in the graph connects a vertex in v1 and a vertex in v2, so that no edge in G connects either two vertices v1 and v2, then v1 or v2. When this condition holds, we can call the pair v1 and v2 as bipartition of the graph set V and G. Okay, I think by the definition you will not be able to get it. Let me explain it to you more properly. See, in a graph, we can have a graph, right? So this is a graph which is representing vertex A, B, C and D. We can also have a graph which is representing vertex A, this is representing vertex B, this is vertex C, this is vertex D. Okay, we can have vertices like this, correct? Now when I'm saying bipartite graph, bipartite, now this bipartite word is meant by bi plus partition. Bi plus partition. Bi means two, partitions you already know. That means can you divide a graph into two partitions? Can you divide the graph into two partitions such that the vertices which are in first partition should not be having any edge between them, correct? Right? For example, here if I say, can I divide this graph into two partitions? No. I'll explain to you what I want to say. I want to say if we can create two sets between the vertices, like there are A, B, C and D. There are four vertices. We can create two sets here. First set may be having some vertices, it can be A and B, for example. The second set may be having some vertices which can be C and D, for example. Now here for these vertices, there can be edge between set 1 to set 2, or there can be edge between set 2 to set 1, but the vertices which are in the first set will not be having any edge between them. For example, this is allowed. There's an edge between A to C is allowed. There's an edge between B to C is allowed. There's an edge between B to D is allowed. These edges are allowed, right? So this kind of graph which we can divide into two sets such that the one set will not be having an edge between them, then that kind of graph is called as a bipartite graph. Now here this is representing a bipartite graph, but this is not representing a bipartite graph, because even if we create two sets which is having A and D or B and C, now between A to B this is also fine, this is also fine, but this should not be there. This should not be there. So this is not a bipartite graph. Let me give you an example of a bipartite graph so that you will be able to understand more clearly here. Assuming that these two graphs are there. Now the best way to identify whether it is a bipartite graph or not is by taking two colors. Assuming that we are marking this as red. Okay, so all the adjacent vertices to G, mark them as green. So this is adjacent vertex to G and this is also adjacent vertex to G, so mark them as green, correct? Now take the next vertex. For example, we discussed with A, so take the adjacent vertices of A, which are F, mark them as red, E, mark them as red, and C, mark them as red. That means all the adjacent vertices of A, you mark them as red. Correct. Then again take the next color, which is the red color. For the vertex F, or take any red vertex, mark all the adjacent vertices as green. So this is the adjacent vertex which is green. Okay, now if we marked all the vertices, now you can try and divide these vertices in two sets. Okay, so the first set for this one will be having G, F, E and C. G, F, E and C. Now there should not be any edge between G, F, E and C. There should not be any edge between G, F, A and C, and the second set will be containing A, B and D. There should not be any edge between A, B and D. If this is happening, then this is a bipartite graph. Now let me try and connect. Okay, between G to A there is an edge, so we connect G to A. Between G to D there is an edge, so we connect G to D. Between F to A there is an edge, F to A there is an edge. Between F to B there is an edge, F to B there is an edge. Between F to D there is an edge, F to D there is an edge. Between E to A there is an edge, E to A there is an edge, E to B there is an edge, E to D there is an edge. Okay, so there are three edges for E also. This is 1, 2 and 3. There are only three edges. For vertex C there are again three edges which are connecting A, B and C. So vertex C is connected with A, it is connected with B and it is connected with D. Okay, now you can see we have created all the edges which are there for this graph, and the graphs and the vertices which are in the same pair, they are not having any kind of edge between them, and this set is also not having any kind of edge between them. So this graph is a bipartite graph. This graph is a bipartite graph. Okay, and this is correct. Now if you look at the second graph, well, let us try to see if it is a bipartite graph or not. Start coloring one vertex with, let us assume, green color. Now all the adjacent vertices, mark them as red. So adjacent vertices A, adjacent vertices E, adjacent vertices B, adjacent vertices D and adjacent vertices C. Now you see the edges, the vertices which are having the same color, they are having an edge between them. So it is not a bipartite graph. It is not a bipartite graph. So bipartite graph will not be having any, the vertices which are having same color will not be having any edge between them. So now you understand what is a bipartite graph. Okay, so the definition is a simple graph if and only is bipartite if and only if it is possible to assign one of the two different colors to each vertex of graph, so that no two adjacent vertices are assigned the same color that we have already seen in the previous example. Okay, now this is just giving some examples of a bipartite graph. Now for example, here in the first graph, this is a bipartite which is K23. K23 means 2 is representing the vertices which are in first set and 3 is representing the vertices which are in second set. Now this is representing K35. There are 3 vertices in first set and there are 5 vertices in the second set. Okay, this is K3, 3 vertices in first set, 3 vertices in the second set. This is K26, 2 vertices in first set and 6 vertices in second set. So bipartite graph will be represented by Kn, M, where the first set will be having n vertices and the second set will be having m vertices, and they can have a number of edges between them. Now that was called as a bipartite graph. Now in the next video, let us look at more concepts related to the graph theory.